When we first introduced chemical reactions, we have said that the molar ratio coefficients that appear before the chemical formula of reactants and products indicate how many atoms or molecules of each reactant must be taken in order to completely use up all reactants, and how many atoms or molecules of the products will be formed as a result. Let us now take a closer look at determining the molar ratio coefficients, also known as balancing chemical equations. The key idea behind balancing chemical equations is that in a chemical reaction, atoms do not appear or disappear, but only rearrange. Therefore, when reactants are completely used up and turn into products, the total number of atoms of each chemical element in the products should be the same as the total number of atoms of that chemical element in the reactants. Consider the example of the combustion of methane. The unbalanced chemical equation of this reaction shows all the reactants and products, but not the molar ratio coefficients for them. Let's count the number of atoms of each element in the reactants in the unbalanced chemical equation. One molecule of methane, CH4, consists of one carbon atom and 4 hydrogen atoms. One molecule of oxygen, O2, consists of 2 oxygen atoms. Hence, the total number of atoms of each element on the reactant side of the chemical equation is as follows: 1 carbon atom, 4 hydrogen atoms, and 2 oxygen atoms. As a result of the hydrocarbon combustion reaction, we form carbon dioxide, CO2, and water, H2O. Let's count the number of atoms of each element in the products for the unbalanced chemical equation. One molecule of carbon dioxide consists of 1 carbon atom and 2 oxygen atoms. One molecule of water consists of 2 hydrogen atoms and 1 oxygen atom. Hence, the total number of atoms of each element on the product side of the chemical equation is as follows: 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms. We can see that the number of carbon atoms 1 is the same on the reactant side and the product side of the chemical equation. But the numbers of oxygen atoms and hydrogen atoms are different. There are 4 hydrogen atoms on the reactant side and 2 on the product side. And there are 2 oxygen atoms on the reactant side and 3 on the product side. We can ensure that the total number of atoms of each element becomes the same on the reactant and the product side of the chemical equation by adjusting the numbers of molecules of the reactants and products. In the unbalanced chemical equation that we are considering, there are 4 hydrogen atoms on the reactant side, enough to build 2 water molecules. So let's place the molar ratio coefficient 2 in front of water. However, we now need 4 oxygen atoms to build a carbon dioxide molecule and 2 water molecules. So let's also place a molar ratio coefficient 2 in front of the oxygen on the reactant side. Now, when we count the total numbers of atoms of each element on the reactant and the product sides of the chemical equation, we find that they are the same. There is still 1 carbon atom in 1 methane molecule on the reactant side, and 1 carbon atom in 1 carbon dioxide molecule on the product side. There are 4 hydrogen atoms in the methane molecule on the reactant side, and 4 hydrogen atoms in the 2 water molecules on the product side. And there are 4 oxygen atoms in the 2 oxygen molecules on the reactant side, and 4 oxygen atoms on the product side, 2 in the carbon dioxide molecule, and 2 in the 2 water molecules. The equation of the chemical reaction is now balanced. A balanced chemical equation is like a recipe. In our example, it tells us that if we take one methane molecule and two oxygen molecules, we will have enough atoms of each type to make one carbon dioxide molecule and two water molecules. And no atoms will be left over. Consequently, if we were to take, say, 200 methane molecules, we could take twice as many, 400 oxygen molecules, and make 200 carbon dioxide molecules, the same number as the number of methane molecules that we started with, and 400 water molecules, twice the number of methane molecules that we started with. If we took 1 mole of methane molecules and 2 moles of oxygen molecules, we could make 1 mole of carbon dioxide molecules and 2 moles of water molecules, and so on. Therefore, the molar ratio coefficients show us the ratios between the numbers of molecules of reactants that we must take in order to use the reactants completely, with none left over, and the ratios between the numbers of molecules of products that we get, as well as the ratio of the numbers of product molecules to the numbers of reactant molecules. That is, how many product molecules we get per reactant molecule. So how does one go about balancing a chemical equation? Well, the first step is to determine how many atoms of each element there are on the reactant and on the product side in the unbalanced equation. For example, if we consider the combustion of propane, C8H18, we see that there are 8 carbon atoms and 18 hydrogen atoms in the propane molecule, as well as 2 oxygen atoms in the oxygen molecule on the reactant side. On the product side, there is 1 carbon atom in the carbon dioxide molecule, 2 hydrogen atoms in the water molecule, and 3 oxygen atoms, 2 in the carbon dioxide molecule and 1 in the water molecule. We then start balancing the chemical equation by balancing the number of atoms that occur in only one compound on both sides of the chemical equation first. In this case, such elements are carbon, that only occurs in propane on the reactant side and in carbon dioxide on the product side, and hydrogen, that only occurs in propane on the reactant side and in water on the product side. There are 8 carbon atoms in a propane molecule and only 1 carbon atom in a carbon dioxide molecule. So we can place a coefficient of 8 in front of the carbon dioxide molecule to balance the number of carbon atoms. There are 18 hydrogen atoms in a propane molecule and only 2 hydrogen atoms in a water molecule. So we can place a coefficient of 9 in front of the water molecule to balance the number of hydrogen atoms. If there are elemental substances in the chemical equation, we balance the numbers of atoms for these elements last. Placing a molar coefficient in front of an elemental substance only adjusts the number of atoms of a single element without affecting the numbers of atoms of other elements. So it is convenient to do when numbers of atoms of all other elements are already balanced. In our example, oxygen is an elemental substance. After we have added the coefficient 8 in front of carbon dioxide and the coefficient 9 in front of water, the number of carbon atoms on both sides of the chemical equation is 8, and the number of hydrogen atoms on both sides of the chemical equation is 18. So these elements are already balanced. However, the number of oxygen atoms on the product side is now 25. 16 in the carbon dioxide molecules and 9 in the water molecules. On the reactant side, the number of oxygen atoms is only 2. To adjust it, we can place a coefficient of 25/2 in front of the oxygen molecule. However, it is the convention that molar ratio coefficients in chemical equations should be integers, that is, whole numbers, not fractions. It makes sense because they show how many molecules of each reactant or product need to be taken, and of course, one can't take half an oxygen molecule, for example. So, if we end up with fractional molar ratio coefficients, as we did in the case that we are considering, we simply multiply all coefficients by the same factor to get whole numbers. In this case, we multiply by 2, and our final balanced equation tells us that we take 2 propane molecules and 25 oxygen molecules, and that allows us to make 16 carbon dioxide molecules and 18 water molecules. This equation is balanced. There are 16 carbon atoms, 36 hydrogen atoms, and 50 oxygen atoms on both sides of it. To summarize, we balance elements that appear in only one compound on either side of a chemical equation first, balance elements that appear as elemental compounds on either the reactant or the product side last, and if we happen to get fractional molar ratio coefficients, multiply all coefficients, including coefficients of 1 that are not written explicitly, by the same factor to get whole numbers.